The observable universe is bounded by the distance that light has traveled since the Big Bang occurred about 13.8 billion years ago. What lies beyond this horizon remains a deeply intriguing mystery. Cosmologists often assume that space-time itself extends infinitely farther than we can observe, and is potentially filled with regions like our own, teeming with galaxies, stars, and planets. However, there is a possibility that these distant regions are different from our visible universe in ways we can't even imagine. One compelling theory suggests a vast and varied landscape where the laws of physics may differ from one another, a concept known as cosmic dispersion. This suggests that constants important to us, such as the speed of light or the strength of gravity, may differ in regions completely inaccessible to our observations. According to another theory, beyond the observable universe lies the cosmic inflationary field, a region where rapid expansion is still underway, essentially pushing the boundaries of space-time and extending the invisible frontier. While these theories beckon to the frontiers of scientific understanding, they also emphasize the limitations imposed by the speed of light and the finite age of the universe, ensuring that some mysteries will forever remain beyond the reach of our telescopes. The limitations that prevent us from seeing beyond the observable universe are due to the very nature of light and the extended timescale of the universe. Our observable universe is defined by the maximum distance from which light has had time to reach us since the Big Bang occurred about 13.8 billion years ago. On the Moon, despite its incredible speed of nearly 300,000 kilometers, the distribution of time is finite. As the universe continues to expand, everything we can see or detect with electromagnetic radiation is in this region, which is currently 93 billion light-years across. Moreover, the world is not static. It has been evolving since its inception. This expansion means that places that used to be close are now farther from our field of view. Light from these regions cannot reach us because the space between us is expanding very rapidly. This expansion is due to dark energy, the mysterious force accelerating the growth of the universe. Even though we have the most sophisticated telescopes imaginable, objects move so far away from us that light cannot fill the space. Therefore, no new moon will come to us to tell us about these noble worlds. It creates a space in the world beyond which lies uncharted space, connected to us by the movement of time and space. Our current observational technology, despite its tremendous advances, suffers from many intrinsic and technical limitations. Telescopes, such as the Hubble Space Telescope, and ground-based observatories such as the Very Large Telescope, have opened up unprecedented views of space, but they still face challenges from atmospheric interference and the inherent dimness of distant objects. Even the latest marvels, such as the James Webb Space Telescope, which works in the infrared to penetrate space dust and record the early stages of galaxy formation, are limited by the light-blocking and distorting effects of the interstellar and intergalactic medium. Future technologies promise to expand our observable universe in revolutionary ways, potentially opening up realms and phenomena that are currently hidden from our view. One interesting area is the field of space telescopes, which are free from the distorting influence of the Earth's atmosphere. For example, the upcoming launch of the Nancy Grace Roman Space Telescope is designed to provide deeper and wider views of space than ever before. Capturing vast portions of the sky in multiple wavelengths will unlock the secrets of dark energy, galactic evolution, and perhaps even detect exoplanets with unprecedented clarity. Moreover, proposed missions such as LUVOIR, Large Ultraviolet Optical Infrared Surveyor, future technology promises to take a giant leap in our ability to observe faint and distant objects, expanding our cosmic horizon. Another revolutionary approach is the use of gravitational wave observatories, based on the pioneering work of LIGO and Virgo. These facilities detect ripples in space caused by cataclysmic events, such as merging black holes, and offer a new way to explore the universe that is not limited to electromagnetic radiation. Future observatories, such as the planned Laser Interferometer Space Antenna, LISA, will search for gravitational waves with even greater sensitivity, potentially revealing details about the early moments of the universe long before the cosmic microwave background was formed. In addition, advances in computing power and artificial intelligence will increase our ability to process and analyze the vast amounts of data these instruments will produce, allowing us to identify patterns and phenomena previously obscured by noise. These technological leaps may open new windows to allow us to understand the nature of space, time, and the universe itself. Exploring the edge of the universe presents many major challenges due to the great distance and fundamental limitations imposed by the speed of light. When we look at space, we also look at the past and see what celestial bodies looked like billions of years ago. This phenomenon of time complicates our understanding as we piece together the story of an ever-changing world. In addition to the inherent limitations of perceptions, there are technical challenges. Even the most advanced binoculars have limited resolution and sensitivity. Faint light from distant objects is drowned out by atmospheric dust, intergalactic wind, and other obstacles that attenuate and distort signals. In addition, our equipment has a limited lifetime and we try to minimize error and noise. Achieving the sensitivity needed to detect faint signals from the edge of the universe requires constant advances in slow technology. For optics and computer algorithms are time-consuming, and these technical solutions are expensive. Finally, there is the problem of data interpretation. Theoretical models often outpace our ability to empirically test them, meaning that our understanding of the edge of the universe and its boundaries is largely speculative. Complex phenomena such as dark matter and dark energy remain elusive, requiring new approaches to detecting them and understanding their nature. Synthesizing observational data with theoretical models is a constant iterative process fraught with uncertainties and requiring international collaboration and innovation. Solving these problems will require not only technological innovation, but also a profound expansion of our theoretical framework and a willingness to explore uncharted scientific territory. The multiverse theory is a provocative idea that suggests that our universe may be just one of a vast, possibly infinite number of universes that make up a great, overarching multiverse. This concept exists in various forms, each proposing a different mechanism for the emergence and coexistence of multiple universes. The best-known option is based on the cosmological principle of cosmic inflation, which suggests that within a fraction of a second after the Big Bang, the universe underwent an exponential expansion. This rapid inflation could lead to bubble universes separating from each other and evolving independently, each with its own physical laws and constants. Another intriguing concept stems from the principles of quantum mechanics and string theory. Quantum mechanics introduces the idea of a many-worlds interpretation, where each quantum event branches off into a new parallel universe. Meanwhile, string theory suggests the possibility of multiple dimensions beyond the usual 3 dimensions of space and 1 dimension of time. According to string theory, different configurations of compactified dimensions can give rise to universes with different properties. Thus, a multiverse could include a vast number of universes, each with its own unique characteristics. Multiverse theory remains largely speculative and controversial, primarily because of the current lack of direct observational evidence. It pushes the boundaries of scientific understanding and philosophical inquiry. forcing us to rethink the very nature of reality and our place in it. If this is true, the implications would be staggering, suggesting that our universe is but a small fragment in a vast, perhaps infinite tapestry of realities. This perspective not only broadens our cosmic horizon, but also forces us to ponder fundamental questions about the existence, causality, and nature of the cosmos. The question of how many universes can exist within a multiverse is more of a theoretical assumption than empirical evidence. Depending on the particular model of the multiverse you are considering, the number of possible universes can range from a very large, finite number to actual infinity. For example, in the context of cosmic inflation, the theory suggests that, in the rapid expansion of space, inflation led to the creation of countless bubble universes, each of which separated to form a separate cosmos. This model does not predict a fixed number of universes. On the contrary, the inflationary process may be perpetual, constantly generating new universes ad infinitum. Similarly, in the field of quantum mechanics, the many worlds interpretation suggests that at every quantum event or decision point, the universe splits, creating parallel universes in which every possible outcome of the event occurs. Theoretically, this branching process could lead to an astronomical, possibly infinite number of universes, depending on the complexity and number of quantum events that occur. Furthermore, the string theory landscape suggests an almost unfathomable number of potential universes, each defined by different values of fundamental physical constants and measurements. These ideas are tantalizing, but they remain speculative and difficult to test with current technology. While there is a compelling mathematical basis supporting these theories, the task of obtaining direct evidence for the existence of other universes remains formidable. To even begin to address these profound questions will require advanced observational techniques, extremely sensitive instruments, and new theoretical discoveries. Whether the true number of universes is finite or infinite, the very possibility expands our view of reality in a way that is both mind-boggling and exciting. Multiverse theories exist in various forms, each proposing different mechanisms by which multiple universes can exist. Broadly speaking, these theories can be categorized into several types, each based on different scientific principles and theoretical foundations. One of the most discussed forms is the cosmological multiverse, which stems from the theory of cosmic inflation. According to this concept, our universe is one of many bubble universes formed during the rapid expansion that occurred a fraction of a second after the Big Bang. Each bubble is a separate universe with its own physical laws and constants, physically separated from all others by regions of inflating space. Another important category is the quantum multiverse, based on the many worlds interpretation of quantum mechanics. According to this interpretation, each quantum event with multiple possible outcomes gives rise to branching universes, where each possible outcome occurs in its own universe. These branches then form a tree-like structure of parallel universes that move rapidly and differ from each other based on quantum principles. String theory also provides a lot of intelligence. This theory suggests that what we think of as our world is a three-dimensional brain floating in higher space. Parallel to our brain, there may exist other brains with completely different physical laws. The interactions between these brains lead to the effects we observe in our universe and can explain phenomena such as the Big Bang. Another option is the theory of a landscape multiverse within string theory, which assumes an almost infinite set of possible vacuum states, each corresponding to a separate universe. The idea is that the constants of nature and the forms of physical laws we observe are just one of many possibilities realized in this landscape of vacuum states. Finally, cyclic multiverse theories suggest that our universe goes through endless cycles of big bangs and big compressions, creating a new universe each time. According to this idea, each cycle may have different laws and initial conditions, creating a sequence of different universes. These different types of multiverse theories, while speculative, push the boundaries of our understanding and force us to consider the deep complexity and potential that lies beyond the horizon of our observations. Each type offers a unique opportunity to explore the true nature of reality and raise questions that could change our understanding of the world. Currently, there is no direct evidence for the existence of a multiverse. However, a number of evidences and theoretical frameworks provide strong reasons to consider the multiple hypothesis. One of the most important pieces of evidence is the theory of global inflation. This theory, which explains the rapid expansion of the universe immediately after the Big Bang, suggests that inflation may have led to the formation of multiple interconnected regions or bubbles of universes. Some variants of cosmic inflation predict that these bubbles form forever, constantly generating new universes. Observational evidence, such as the uniformity and flatness of the cosmic microwave background radiation, supports the idea of inflation. And while this alone does not prove the existence of the multiverse, it does make the concept more plausible under inflationary scenarios. Another line of indirect support comes from quantum mechanics, in particular the multiple worlds interpretation. This interpretation offers a solution to the quantum measurement problem by assuming that all possible quantum measurement outcomes do occur, each in its own branching universe. Although this interpretation is purely theoretical and cannot be experimentally verified, it is consistent with the mathematical formalism of quantum mechanics and has a growing following in the physics community. The anthropic principle is another consideration that comes into play when discussing the multiverse. He notes that the physical constants of our universe appear to be fine-tuned for the existence of life. In a multiverse, with a vast or infinite number of universes, each with different constants, the anthropic principle suggests that we are in one of the rare universes where conditions are just right for life. While not a direct proof, it provides a potential explanation for why our universe seems so incredibly suitable for life. Finally, theoretical concepts such as string theory offer a landscape of possible vacuums, each corresponding to a different set of physical laws or constants. This landscape theory of the multiverse implies that our universe may be one of an almost infinite number of possible states of the vacuum. This idea is gaining momentum as string theory seeks to become the fundamental theory of all things and suggests that a single unique universe may not be the most natural or inevitable outcome. While this circumstantial evidence and theoretical support is compelling, it still cannot serve as concrete proof. Future advances in observational techniques, a deeper understanding of quantum mechanics, and breakthroughs in fundamental physics are needed to provide better answers to the exciting question of whether we are part of a larger multiverse. The interaction between different universes within a multiverse is an intriguing topic, and its possibilities vary greatly depending on the particular multiverse theory. Generally speaking, different universes are often considered causally disconnected, meaning that they do not interact with each other in any observable way. However, some theories suggest mechanisms by which some form of interaction or influence, however indirect or minimal, is possible. In the cosmological model of a multiverse resulting from cosmic inflation, bubble universes are generally separated by regions of inflating space, making direct interaction virtually impossible. However, some hypotheses suggest that if two bubble universes collide, it could leave noticeable imprints on the cosmic microwave background, CMB. These imprints may manifest themselves as unusual patterns or anomalies in the CMB data. This collision scenario is still hypothetical and not supported by observational data. In the case of the large universe, this arises from the multidimensional interpretation of quantum mechanics. These branches are not mutually exclusive. Because worlds are independent in their own way, there is no conceptual framework that supports the interaction between them. Each world evolves independently, with its own unique events and history that no one else can see. The multidimensional brain world inspired by string theory offers another exciting possibility. According to this theory, our universe is a three-dimensional brain floating in a higher dimension. Parallel to our brain, other brains exist in this three-dimensional space. In some cases, interaction between brains may be possible and may explain some aspects of the dynamic world. For example, collisions between brains could create a new universe and trigger an event similar to the Big Bang. While theoretically exciting, these interactions remain purely speculative and inaccessible to modern experimental verification. Another interesting direction is the concept of quantum entanglement between universes within a multiverse. Some speculative theories suggest that entangled particles may maintain connections between different branches of a multi-world multiverse. This intriguing idea hints at possible subtle influences or correlations that could manifest in surprising ways, although it remains largely untested. In general, although some theories suggest possible interaction mechanisms, most multiverse models assume that the different universes remain isolated, evolving independently of each other. Confirming any form of interaction, direct or indirect, between universes will require significant breakthroughs in both theoretical physics and observational technology. Until then, the potential for interaction remains an open and fascinating question in the study of the cosmos. Brain cosmology is a fascinating framework within string theory and its higher dimensional offshoot, M-theory. At its core, brain cosmology posits that our familiar four-dimensional universe, consisting of three spatial dimensions plus one dimension of time, is actually a three-dimensional brain floating in a higher dimensional space, often referred to as the three-dimensional brain. These extra dimensions are usually compacted or hidden, making them invisible to our everyday experience. In this context, the word brain is derived from the word membrane, indicating that our world is only one of its masses. In the brain world, other brains coexist in this higher world, each with its own set of rules and physical characteristics. One interesting aspect of this theory is that while the electrical forces and other interactions known to the brain are finite, energy is not. Gravity can extend over a large space, which helps explain why it is much weaker than other basic economies. Of course, this force dissolves it into different parts. The brain planet opens the door to exciting possibilities, such as the possibility of brains colliding in the bulk. These collisions lead to Big Bang-like events and create new universes. For example, cyclic or ekpyrotic models of the brain universe suggest that our universe may go through infinite cycles of expansion and contraction due to brain collisions. Each match can reset world time, lead to a major success, follow it, and so on. While these ideas are intriguing, they are difficult to test directly. However, there are also tantalizing consequences that can be observed or deduced indirectly. For example, some cosmological models predict that brain collisions may leave imprints in the cosmic microwave background or affect the distribution of galaxies and large-scale structures in the universe. Another potential area of research is the detection of higher-dimensional gravitational waves, which could reveal new information about the volume space and interactions between brains. While brain cosmology remains a highly speculative and mathematically complex field, it offers profound insights and challenges our understanding of space, time, and the very nature of the universe. It pushes the boundaries of traditional cosmology and opens up new areas of research that could fundamentally change our perception of reality and our place in the cosmos. The brain is a fundamental component of string theory and its extension, M-theory, which have revolutionized our understanding of superspace. Within these concepts, the brain, or shorter membrane, is a multidimensional object that can be extended in different spatial dimensions. For example, a one-dimensional brain is a string, a two-dimensional brain is a membrane, and a three-dimensional brain is a three-dimensional brain, according to some philosophers of our world. These brains are embedded in a multidimensional space called a volume. Beyond the three places and times we encounter every day, there are many dimensions of volume itself. According to string theory, our entire universe can be thought of as a three-dimensional brain running through this high space. One interesting aspect of the brain theory is how it solves the problem of verification in physics, especially why the gravitational force is weaker than other basic equations such as electronics and energy. According to brain theory, although other forces are present in the brain, energy can be distributed throughout the brain. This flight into higher dimensions may explain why we see weak energy. It is diluted by many elements beyond our visible world. Higher worlds can be accessed by multiple brains, which can lead to multiple worlds inhabited by different brains. These worlds may have their own physical laws and stability. Events and interactions in the brain in this multifaceted area lead to the phenomena we see in our world. For example, according to one hypothesis, the Big Smoke may be caused by the collision of our three brains with another brain in the Big Book. This event injects tremendous energy into our brains, creating the perfect conditions for the Big Bang. Another interesting consequence of the existence of brains and higher dimensional space is the possibility of detecting phenomena arising from these extra dimensions. This may include the identification of gravitational waves resulting from interactions in bulk space, or the observation of imprints in the cosmic microwave background that point to a deeper structure of space-time. Advanced theoretical and experimental work, such as the search for microscopic black holes or the study of large-scale cosmic structures. Ultimately, this could provide empirical clues about the higher dimensional landscape of the brain. Brains are multidimensional entities encapsulated in a higher dimensional volume, offering a framework that expands our understanding of space, time, and gravity. They serve as a bridge between familiar physical laws and the exotic possibilities lurking in dimensions beyond our perception. This conceptual leap opens up a wide range of scientific research, pushing the boundaries of modern cosmology and theoretical physics. Direct evidence for brain cosmology, like much in modern theoretical physics, remains elusive due to the extreme difficulty of verifying phenomena occurring on energy scales or in dimensions far beyond current experimental capabilities. However, several pieces of circumstantial evidence and theoretical motivations support the viability of brain cosmology as a compelling framework. One key area of indirect support is the coherence of brain cosmology within the broader context of string theory and M-theory. These systems aim to unify the fundamental forces of nature, including gravity, in a higher dimensional environment. String theory, according to which particles are actually tiny vibrating strings, naturally incorporates multidimensional brains into its mathematical structure. Brain cosmology helps solve some perplexing questions in physics, such as the hierarchy problem, the puzzling question of why gravity is so much weaker than other fundamental forces. By proposing that gravity leaks into extra dimensions, brain cosmology provides a plausible mechanism for this discrepancy. Another aspect is the understanding of the initial conditions of the universe that brain cosmology provides. For example, some models, such as the ekpyrotic or cyclic model of the universe, suggest that catastrophic events such as the Big Bang may be the result of collisions between brains. These models can elegantly explain the homogeneous and isotropic nature of the cosmic microwave background radiation and the distribution of large-scale structures in the universe. Moreover, cosmological observations provide subtle hints that may be consistent with predictions of brain cosmology. While the current observational evidence does not yet directly support the existence of brains or higher dimensions, it does offer intriguing anomalies. For example, some features of the CMB, such as unexpected temperature fluctuations or alignments, can potentially be interpreted as signatures of brain-to-brain interactions or higher dimensional processes. In addition, the search for gravitational waves has opened a new frontier, where waves may one day be detected emanating from dimensions beyond the three we observe. Finally, particle physics experiments, such as those conducted at the Large Hadron Collider, can provide indirect clues. The discovery of particles whose behavior is consistent with the existence of extra dimensions, or the observation of high-energy phenomena indicative of interactions beyond the standard model, can confirm brain cosmology. For example, the appearance of microscopic black holes or particles with characteristics predicted by string theory would support the theory that higher dimensional brain models exist. Although direct evidence for brain cosmology is currently lacking, various theoretical and observational possibilities provide compelling indirect support. Continued improvements in both experimental techniques and theoretical models may eventually provide the empirical evidence needed to substantiate this intriguing concept. The search for answers to these questions pushes the boundaries of our understanding and continues to challenge and refine our perception of the universe. The idea that brains can collide and create universes is an interesting aspect of brain cosmology, especially in the context of string theory and M-theory. This concept is central to some theoretical models, such as the ekpyrotic and cyclic models of the universe, which suggest that our universe was born from such a monumental event. In brain cosmology, our observable universe appears as a three-dimensional membrane, or three-dimensional brain, embedded in a higher dimensional space, known as the bulk space. Other brains may exist in parallel with ours within this mass, each with its own set of physical properties and characteristics. Collision theory suggests that these brains are not static. They are moving or oscillating in a higher dimensional volume. When two brains get close enough to each other, they can collide. This collision could be an incredibly energetic event. In the equi-brain model, collisions between brains are proposed as an alternative to the traditional Big Bang theory. According to this model, the collision of these brains releases an enormous amount of energy, essentially resetting the conditions of the universe and initiating a period of rapid expansion similar to the inflationary period in traditional cosmology. The consequences of this collision of brains will set the initial conditions necessary for the formation of a new universe. This collision could result in a hot, dense state that expands and cools, leading to the formation of matter, galaxies, and other cosmic structures. The energy released could have created the ingredients needed for the Big Bang, generating the radiation, particles, and forces that eventually gave rise to the cosmos as we perceive it today. One intriguing aspect of this theory is that it offers potential explanations for some of the observed features of our universe. For example, the homogeneity and isotropy observed in the cosmic microwave background radiation may be a natural result of the brain collision process. In addition, this model may provide an explanation for the large-scale structure of the universe and some aspects of cosmic evolution that are difficult to explain using classical Big Bang theory alone. Experimentally detecting brain collisions or testing this model is very difficult. However, some theoretical predictions can provide indirect clues. For example, certain patterns or variations in relic radiation could indicate such a meeting. In addition, shield waves generated by high-energy events in a large-scale volume may provide indirect evidence for the collision hypothesis. The idea that brains collide to create a new universe represents a revolutionary view of the origin of our universe. Despite its deep theoretical underpinnings and the difficulty of direct verification, it offers new and exciting possibilities for understanding the fundamental nature of reality and the underlying processes that govern the birth and evolution of universes. As observational and experimental techniques evolve, we may come closer to unlocking the mysteries of brain cosmology and the true nature of the origin of our universe. In the fascinating realm of brain cosmology, the apparotic model provides an unusual and startling alternative to the generally accepted Big Bang theory. This model, whose name comes from a Greek word meaning ignition, suggests that our universe was born not from an explosive singularity, but from a cosmic collision in a higher dimensional space. Imagine a vast multidimensional space in which our familiar three-dimensional universe is just one of many brains soulfully floating through this insurmountable space. These brains may collide from time to time, and it is this collision that the equipartition model considers to be the origin of our universe. Such a conceptual scheme is remarkably intricate, and indicates that the energy released by the collision with the brain caused the hot, dense, and rapidly expanding state that we associate with the birth of our cosmos. This model has intriguing implications for some of cosmology's biggest mysteries, such as the observed homogeneity of the cosmic microwave background radiation and the formation of large-scale structures in the universe. Incorporating the principles of string theory and high-dimensional space, the ekpyrotic model seeks to provide a more complete understanding of the origin of our universe, forcing us to think beyond conventional boundaries and comprehend the mysterious brain dance that may underlie the cosmos we observe today.